Picture a long stretch of sidewalk, a strip of pavement running between two buildings. It starts to rain hard, and you have an unlimited supply of floating umbrellas in every size you can imagine. You start tossing them up over the sidewalk, hundreds, thousands, as many as it takes until every single inch of pavement is shielded by at least one umbrella and not a single raindrop reaches the ground. The sidewalk is dry. Now I ask you a question. Can you walk back along that sidewalk, point at almost every umbrella, dismiss it, and still have a dry sidewalk underneath only 6 or 12 or 100 umbrellas? Finitely many. Let's answer this and more after the break. Welcome back. For some sidewalks, the answer is yes. No matter how messy the umbrellas were thrown, there is always a finite few that already do the whole job. For other sidewalks, the answer is no. There is a way to throw the umbrellas so that you genuinely cannot remove any without leaving a wet spot somewhere. The sidewalks where the answer is always yes have a name. They are called compact. Apostol writes this as definition 3.30. A subset S of Rn is compact if and only if every open covering of S contains a finite subcover. That is, if F is a collection of open sets whose union contains S, then there is a finite subcollection of F whose union also contains S. What does that actually mean? It means cover the set with open balls however you want. Use 1,000, use uncountably many. The set is compact when you can always toss out almost all of them and keep the set covered with only finitely many balls remaining. That's statement A, the umbrella sidewalk. The first face of compactness, and it picks up exactly where we left off last video. Last video, the Heine-Borel theorem said, if a set is closed and bounded, every open cover reduces to a finite subcover. So closed and bounded sets are already compact. The question this video is asking is, are there others? And what does this property really mean? Hold statement A in your head. Now Apostol gives a second statement, a geometric one. And on its face, it sounds completely unrelated. Statement B. A subset S of Rn is compact if and only if S is closed and bounded. Closed in the sense that S contains all its accumulation points. Bounded in the sense that S is contained in some n-ball, B, A, R, of finite radius. What does that look like? A fortress. 2 rules. Rule 1. The fortress has to end somewhere. You can throw a giant net over the entire structure, every wall, every tower, and the net is finite. There is no wing of the castle that runs off to infinity. That is bounded. Rule 2. The fortress has no missing bricks. The outer wall is solid. If you walk a sequence of points up to the boundary, the point you arrive at is part of the fortress, not floating in empty air just outside. That is closed. A leaky bucket fails Rule 2. An infinite road fails Rule 1. A fortress passes both. So a compact set, geometrically, is a fortress. That's statement B. Hold that too. And then Apostol gives a third statement. This one is, the strangest of the three. Statement C. A subset S of Rn is compact if and only if every infinite subset of S has an accumulation point that lies inside S itself. What is that even saying? Picture a sealed glass jar. Drop infinitely many fireflies inside. The jar is not growing. The fireflies cannot escape. So they have to crowd. Not might, have to. Somewhere inside that jar, there is at least one location where the fireflies are bunching so densely that any tiny neighborhood you draw around it, however small, still contains infinitely many of them. That cluster point is the accumulation point. And statement C says, in a compact set, that cluster point lives inside the jar. Not on a glass wall that doesn't exist. Not floating outside in the void. Inside. That's the third face. The firefly jar. 3 statements. Coverings of umbrellas, the geometry of a fortress, the crowding of infinite fireflies. These look like they belong to 3 different subjects. They are the same theorem. Apostol's theorem 3.31. In Rn, statements A, B, and C are logically equivalent. Any one of them forces the other 2. The umbrella sidewalk and the fortress and the firefly jar describe the exact same kind of object. A set in Rn with this property is called compact. By definition 3.30, the official definition is statement A. By theorem 3.31, the other 2 follow automatically. Now we prove it. The book splits the argument into 3 arrows. We already have one of them from last video. Heine-Borel told us that closed and bounded implies every open cover has a finite subcover. So statement B implies statement A. That's locked in. We need 3 more. A implies B, B implies C, C implies B. Let's do them. First arrow, A implies B. Compact implies closed and bounded. Bounded first. We are inside a compact set. Pick any point P in it. Around P, draw a ball of radius 1. Then a ball of radius 2. 3. 4. A nested infinite ladder of expanding balls. Every point of the set sits at some finite distance from P. So every point of the set is inside some ball on this ladder. The ladder is an open cover. Now compactness fires. The cover collapses to finitely many balls. The set fits inside the largest of those balls. The set is bounded. Now closed. This one is sneakier. Suppose, for contradiction, that there is an accumulation point Y sitting just outside the set. Every neighborhood around Y dips into the set and pulls out a point. Y is right up against the wall, but not in. Now around every point X inside the set, we draw a small open ball. We pick its radius to be exactly half the distance from X to Y. So this ball stretches from X toward Y, but never reaches Y. It always stops halfway. We do this for every single X. The result is an open cover of the set. Compactness fires again. Finitely many of those little balls already cover the entire set. Take the smallest radius among them. Call it R. Now look at the ball of radius R around Y itself. By construction, every fortress ball stops more than R away from Y. So the ball around Y misses every one of the finitely many fortress balls, which means it misses every point of the set. But wait, Y was supposed to be an accumulation point. Every neighborhood of Y was supposed to contain a point of the set. we just found one that contains none. Contradiction. Y cannot be outside. Every accumulation point sits inside. The set is closed. 2 arrows down. Compact gives closed. Compact gives bounded. Now the middle arrow. B implies C. Closed and bounded implies every infinite subset clusters inside. Take any infinite subset T of our fortress. T sits inside the fortress is bounded, so T is bounded. We have, in effect, infinitely many fireflies trapped in a finite jar. The Bolzano-Weierstrass theorem from earlier in this chapter takes over from here. Every bounded infinite set in Rn has an accumulation point, so T has one. That accumulation point is also an accumulation point of the fortress, since T sits inside the fortress. And the fortress is closed. Closed sets contain all their accumulation points, so the cluster point lives inside. This is the firefly argument made formal. Bounded says the jar is finite. Infinite fireflies in a finite jar must bunch up somewhere. Closed says the spot they bunch at is part of the jar, not a hole in the wall. The cluster lands inside. Final arrow. C implies B. If every infinite subset clusters inside, then the set is closed and bounded. Bounded first. Suppose, for contradiction, the set is unbounded. Then for every positive integer m, we can find a point x sub m in the set whose distance from the origin is bigger than m. So we have x sub 1 farther than 1, x sub 2 farther than 2, x sub 3 farther than 3, on and on. That collection is an infinite subset. By assumption, it has an accumulation point y inside the set. But here's the problem. The triangle inequality says the distance from x sub m to y is at least the distance of x sub m from the origin minus the distance of y from the origin. Once m is bigger than the distance of y from the origin plus 1, the distance from x sub m to y is bigger than 1. So only finitely many of our x sub m sit within distance 1 of y, not infinitely many. Y cannot be an accumulation point of those points. Contradiction. The set must be bounded. Closed next. Take any accumulation point x of the set. We need to show x is actually a point of the set, not just sitting near it. Around x, look at shrinking balls. Radius 1, then 1/2, then 1/3, 1/4. Each ball smaller than the last. Each one contains a point of the set because x is an accumulation point. Pick one fresh point from each ball. Call them x sub 1, x sub 2, x sub 3, on and on. They are all in the set. They are all distinct. They form an infinite subset. By assumption, this infinite subset has an accumulation point in the set. Now where is that accumulation point? The points we're squeezing in toward x by construction, so x is the only place they can pile up. The accumulation point is x, so x is in the set. The set is closed. 3 arrows. A implies B, B implies C, C implies B. Combined with Heine-Borel from last video, the triangle locks. All 3 statements collapse into one. Compactness. The reason this property dominates the rest of analysis is because on a compact set, the things that go wrong elsewhere stop going wrong. Continuous functions reach their maximum and their minimum. Sequences always have convergent subsequences. Open covers always shrink to finite covers. Nothing runs off to infinity. Nothing falls through a hole. Compact sets are where the rules behave. And go back and watch last video with this idea in your head. Lindelof, Heine-Borel. Those covering theorems were not isolated results about open balls. The work you did there, taking arbitrary open covers and squeezing them down to finite subcovers, that was already compactness. We just had not named the property yet. Last video built the room. This video told you what the room is called. But everything we did today used the Euclidean ruler. Distance squared, square root of the sum, all of it. What happens if our points are not vectors in Rn? What if they are functions, or sequences, or shapes in some other space where the meaning of distance has to be invented? That's the next move. Metric spaces. See you there.